Okay, thank you everyone for being today in this seminar. Our guest is Dr. Azadeh, and I'm sorry, I can't pronounce maybe your last name correctly. How do you say your
Haghighi.
last name?
Haghighi. I think the closest
Haghighi.
people can get to that is Haghighi, which is totally fine. Yeah.
Haghighi. Okay, I just know you as Azadeh from
Yeah.
years back. So,
Mhm.
so Dr. Azadeh today will present advanced computational tools for smart additive manufacturing, model-based, data-driven, and beyond. Dr. Azadeh received her PhD from University of Illinois Chicago and a master's degree from the KTH institution in Sweden and a bachelor degree from Sharif University of Technology in Iran. She is the director of Smarter Lab at the Mechanical and Industrial Engineering Department at UIC. She serves as the Associate Editor for the Robotics and Computer Integrated Manufacturing Journal and on Advisory Board of Journal of Manufacturing and Materials Processing. Her research has been supported, among others, by the U.S. Department of Commerce, the National Institute of Standards, and has been supported by the Illinois Manufacturing Excellence Center. Her research interests lie at the intersection of smart, advanced, and sustainable manufacturing. She is the recipient of the Society of Manufacturing Engineers Outstanding Paper Award, the IMEC Future of Illinois Manufacturing Faculty Award, and the UIC Provost Award for Graduate Research. So please join me in welcoming Dr. Haghighi today for our seminar, and thank you for having the time to present your research for us.
Sure. Yeah. Thank you again for having me. Super excited here, and thanks all for the kind introduction. The talk, as you mentioned, the title of that is Advanced Computational Tools for Smart Additive Manufacturing, Model-Based, Data-Driven, and Beyond. And hopefully I can basically say a couple of interesting stories, for everyone here, and tell about like the efforts that my group actually is dedicating on the smart manufacturing topic in general. So I'm sure everyone here is familiar with additive manufacturing, so I'm not going to go into details, and just a short recap on the technology. We know that it has created a lot of like capabilities when it comes to innovation of new products and designs and everything, especially when you have complex features or heterogeneous compositions and all that. So additive manufacturing has shown the promise in those applications. And it is with no doubt that we have seen like a market value growth of the technology, and it has been projected to go beyond like 20-something billion by 2025. So this is very significant and also exciting for the researchers. Now, we know that since its emergence in the 1980s, additive manufacturing mainly used for making prototypes and all that, and it has kind of been changing throughout the years. Especially recently, we have seen this trend that the additive manufacturing technology and products are now being used in critical industries like aerospace, defense, and it is with no doubt that ensuring the final quality of these parts is becoming more serious than ever before. No one wants like a jet to kind of drop middle of the sky, right? So the technology, in a sense, is still not very mature. There are still issues with the quality of the parts that are being printed. For example, we see frequent voids and pores that are happening inside the specimens, and these are critical because these are generally the regions that crack can initiate and propagate eventually. We have surface roughness issues associated with parts that are printed with this technology, and then deformations and distortions which can impact the conformance of the parts to like their tolerances. These are generally due to the cyclic patterns of the heat. So we have heating, cooling, and then shrinkage expansion cycles that can eventually deform the part or distort the part. So yes, there are a lot of issues, but from like a researcher's point of view, this is exciting news and good news. Basically, we have stuff to really work on and help promote the technology and enhance the technology as it is. So throughout the years, my research group has been working on basically addressing the different aspects of quality in additive manufacturing, ranging from micro levels to macro levels, and also from process level to product level. And today in this talk, actually, I have selected three of our like specific like topics ranging from this process to product level that our group has worked on. And one is on film and bonding porosity variation modeling. The other one is surface roughness modeling, and the third one is on the product level, so it deals with the tolerance design and process planning. And as you see that these three topics actually match the three different quality issues that I mentioned with respect to the additive. And after I talk about these works that we have done, I want to say, or basically paint the picture for you of what is the vision for smart additive manufacturing, where we're really going. So when it comes to real-time quality assurance, what is the future of additive manufacturing, what are the challenges ahead, and how our research group is actually trying to address those challenges. So with respect to the film and bonding and porosity, as I said, these are really important factors because they can impact the mechanical properties of the parts in the first place. And they are not generally desirable to have like pores or voids inside the part. So there is a lot of work, to characterize the bonding and porosity, especially when it comes to extrusion-based additive manufacturing. Then we have also bonding of layers. So formulating this bonding and porosity is important to not only understand the global properties of parts like the tensile strengths or all these different properties at the global level, but also understanding the localized properties of parts. So for example, in the specimens that you see, these are the same specimens printed with different like path planning methodologies, and you see that the voids or the pores that are happening inside the specimens, like you see the spatial variation or distribution, not just along the deposition path, but also along the build direction. So it is important to kind of characterize that spatial variation of both void and bonding. Now by bonding, I mean basically the extent of the two paths being connected to each other. So in extrusion-based additive manufacturing, you have two paths that are being deposited. Now, if they're close enough, they generally can start forming some bond, and this is like thermally induced and also induced by the surface tension. And the bonding, of course, specifies how strong the properties would be, but also the pores contribute to the mechanical properties. So understanding, as I said, the spatial variation of both the bonding extent and the void is important. Now, the one thing that is really impacting this spatial variation is, of course, the localized thermal profile that is different. And of course, a lot of researchers are trying to address that and characterize that through numerical methods or data-driven approaches, etc. Another factor that actually at the time was not really considered was the bead deformation. So each of the paths that are being deposited, they can deform due to stress, creep, or gravitational forces, or even the weights of upper layers. And the deformation also contributes to the spatial variation of the voids and bonding. So we were thinking of how we can incorporate that bead deformation into our modeling. And of course, it's something that if you want to numerically formulate that, it's very complex in nature. So we decided to go with data-driven approaches. So this was a framework that we proposed. Of course, we had to have some form of thermal profile modeling. So we used numerical simulation for that. Then we used the Newtonian sintering model for characterizing the bonding. And this is a very popular model. It's already there in the literature for many years. However, we decided to actually look at the cross-sectional images of the specimens that were printed and try to extract the data related to the microgeometry to basically establish or find a relationship of the prints with the bead geometry deformation and incorporate that information into the bonding formula that we had after the Newtonian sintering model. So using the law of the conservation of mass, we could actually update the boundaries for the voids and the bondings as well, and then come up with a more accurate representation of this spatial variation of these two elements. So this is again a little bit more details of the different steps that were involved in the methodology. So up to here, it's pretty much like somehow like standard from the literature. Of course, we had this numerical thermal profile where it was actively updating a temperature or a thermal tensor I've used MATLAB actually. It was actively checking at the active neighbors and the contact areas to update the temperature. And then that was fed into the theoretical model, that temperature, to formulate the bonding. And then we had a neural network that was formulating the bit geometry deformation. And finally, a geometric model for the void boundary update that would give us the updated value for the bonding and the voids, basically areas. This actually just shows you the results of this work. So of course we had to compare with experiments. So here the orange ones are our predictions. So you see that on the left we have both the dimensionless interlayer and intralayer necking radiuses. So not just the bonding with the adjacent filaments on the same layer, but with the layers on the top or the bottom as well. So that's represents the interlayer and intralayer necking radius. And blue one is the experiment, and you can actually see that the orange one, basically, which is a proposed method, is very close to the blue experiment data. The black one, which is scenario one, is actually the output of the Newtonian sintering model. So this is if we didn't incorporate for the bit deformation, you see that we couldn't really capture the real or the actual spatial variation correctly. So by incorporating the bit geometry, we could actually enhance the prediction significantly. And on the right side, you also see so this was the necking radius, and here on the right, you can see some of our validation results with respect to the void area. And we were just randomly selecting some voids, using image analysis to get the area solved, and then compare it with our proposed model on the bottom. And you see that there was pretty much like a good match between the two here. So this was on the basically the bonding and the pore characterization. Now moving on to the surface roughness characterization, we know that surface roughness is an issue in additive manufacturing, and many people actually use hybrid processes by, for example, incorporating additive and subtractive like milling together to enhance the surface roughness, and this is a very powerful tool. Now, one thing that was not really available at the time was, any kind of like theoretical model for the surface roughness as a result of a hybrid process. And this is important because we want to understand the capability of our process in the first place and see, for example, how much we can enhance the surface roughness by using this hybrid process, and how much, for example, of like processing, like using the CNC milling would be enough for us to achieve the roughness we would eventually want. So to basically address this gap, we came up with this theoretical model for surface roughness modeling. Here, similar to the previous study, we wanted to basically leverage some insights from the actual physics of the process. So for example, in the previous one, we knew that based on some domain knowledge of the process, the bit deformation contributes to this like a spatial variation. So we wanted to leverage that information. The same idea here, we wanted to get some insights from the process physics. And here we actually leveraged the knowledge we had on the staircase effect and how that would kind of create some like different patterns of surface profiles for the print, as you can see, for example, on the middle image here. So when you have a printed surface, you see that due to the staircase error, you have these stairs, and that's those staircases actually are contributing to the surface roughness. And again, based on experimental results and all that in the literature, we know that they are mainly a factor of layer thickness and orientation, right? So we, of course, in our theoretical modeling, we had to incorporate those parameters in. So the idea that we followed here to theoretically formulate the surface roughness was that we want to have a theoretical model for the surface profile in additive, and also have a theoretical model for the surface profile in a subtractive process, here specifically milling process. And then if we intersect these two together, right, whatever mathematical function we can get as intersection of these two would be the intersected profile, which is the profile that can be achieved by this hybrid process. And if we can get that, then you can actually easily calculate the surface roughness using this formula. So that was the core idea. So we need to have a representative formula for the surface profile in additive. We used this unit geometry, so that's a parabolic function and this line. So together it was a unit geometry, so repetition of these unit geometries would give us the surface profile. And of course we could mathematically formulate this parabolic function and this line together. And then for the subtractive process here, specifically milling, we found that the closest mathematical function we can find is a sawtooth function, as you can see here. So that was selected as basically a unit geometry representation for a subtractive process here, milling. And then depending on different stratification angles, we had to consider different cases for the mathematical computation. So for when the stratification angle was equal to 90 degrees, so you see the bold line, basically this bold or thick function represents the intersected profile, which is the function we want to find eventually. And the finding this profile can be actually reduced to finding these intersection points. So you can see that if you know these intersection points that I've highlighted here, then you would easily get this the function of this intersected profile, because it kind of goes back and forth between the parabolic function and the sawtooth function, right? So that was the problem that we were eventually interested in. And of course, each of these functions we had to convert to periodic functions. So we used Fourier transform to do that, to convert each of them to periodic functions and then eventually intersect them. Get these intersected points solved using an algorithm that we developed. And eventually after that, it was all solved. We could easily get the surface roughness solved. So I don't have the formula for that here because it was a long formula, but you could easily solve it afterwards. For when the stratification angle was between 0 and 90, again, we had to split it into two different cases depending on where the milling profile was positioned. If it was here or here, then the formulation was slightly different. But again, the whole idea was still the same, intersecting them, finding the mathematical function of the intersected profile and getting the surface roughness solved. So I'll just jump to the results here quickly for you. So of course, we didn't have a hybrid machine. We actually developed our own robotic arm for additive subtractive manufacturing. So I mean, it required oh, it's okay. So I don't know what happened. Okay. So it required some coding. We had our own MATLAB code, some coordinate transformation to convert the geometries and the G code from the slicer to the robot coordinate system and all that. And then the robot was equipped with a subtractive head and additive manufacturing head that we also developed together. We had this geometry that we designed. The reason we designed it this way was that it had a range of stratification angles so that we can kind of test and validate the efficiency or of accuracy of our proposed approach. And of course, there were parts of some of the parameters in our model that we had to experimentally fit and get them out because, for example, they were associated with the errors of that specific machine or process. So like, for example, these epsilon X and Y, so we could extract them from the actual prints under the microscope. And eventually we used the optical profiler to get the surface roughness out. And here you see, for example, for different stratification angles, how our model, theoretical model actually could do compared to the experimental data. So there was still like a close match between them. So that's the robotic one. So now I want to jump to and the product level. So this paper, I mean, or this study, including and as well as the previous one, they were both on the process level. And now I want to go to the product level. So now here we're dealing with different parts and a final product. And sometimes, you know, the parts have to be put together, assembled together. And I know additive manufacturing has potential for making non-assemblies, but it's still eventually all the parts in real world, you know, there might be some assemblies involved. And for that, understanding what are the consequences at the product level is also important, and what type of research can be done at the product level. So traditionally, tolerance design has been used as a very powerful tool to not just minimize the defect rate, but also the manufacturing cost. So the way people traditionally do tolerance design is that they come up with some like cost tolerance functions that are kind of experimentally fitted, and then they use it at the design stage to come up with the right tolerances that are assigned to different parts. And again, the whole point is to minimize the defect rate of the final part and ensuring that the final product will have the functionality that it needs. Now, in these type of like studies and traditional manufacturing, there are certain assumptions when it comes to tolerance design. For example, you need to have some good understanding of the probability distribution of the errors and the variabilities that are associated with the process. So this is something still not fully not fully known for additive, okay? So in traditional manufacturing processes, generally based on the central limit theorem, one can assume normal distribution for the error. And that's understandable because the scale of production there is like mass production. So you're dealing with fabricate or making parts that are, you know, hundreds or thousands of parts, right? So you can easily go with the central limit theorem and assume normality of errors, and then all of the calculations still looks sound. But those assumptions are not valid for additive manufacturing anymore, because in additive manufacturing, we're not dealing with mass production now. We're dealing with mass customization. So we're not interested in making thousands of parts, but maybe 1, 2, 3, or just a small batch of certain geometries and then moving to another set of geometries. So it is clear that the traditional tolerance design approaches might not be basically useful anymore, and the assumptions of those are not also valid anymore. So there should be some way to kind of do tolerance design for additive manufactured parts with consideration of the new circumstances of additive manufacturing. Also, in traditionally, tolerance design is done separately at the design stage, and then the tolerances are transferred to the manufacturing stage, and then the manufacturer will just decide what process parameter, for example, just based on experience or some guidelines, would go best to achieve that tolerance, okay? For additive, again, I don't think this is a good approach. So the ideal approach would be something that does the design and manufacturing jointly together. So that was actually what inspired us to do this following study, to see, okay, can we do joint tolerance design and process planning for additive manufacturing, and how we can do that specifically because, especially since in additive we have basically a mass customization domain. So we don't have like a lot of data to basically extract, for example, functions or after the probability distribution of the errors and etc. So we have to rely on a small number of data points to kind of get inspiration or ideas about the probability distribution of the error, and then use that for tolerance design, as well as making decisions on what type of process parameters should be used for 3D printing. So that was what inspired us for this project here. And another thing that we wanted to leverage is that in additive manufacturing, you see frequent systematic shifts, both positive and negative shifts. And from a design standpoint, someone might say, okay, if I have a shift, I can easily compensate it, right? I can do design adjustments. I can change the nominal size, for example, or for example, I can tune my parameters to kind of avoid or eliminate this shift. However, we can actually leverage the shifts still, right? So by keeping the shifts as they are and basically allowing tolerances to have a form of asymmetric, whereas symmetric, which are the traditional ways that tolerances are defined, we can still leverage, we can still manage to get assemblies that are conforming and have functionalities, because we might be able to select the parts in a way that the shifts cancel each other out. So you will still get the functionality you need, right? And this is still going to be cheaper than, for example, going with any type of compensation or, for example, any kind of other fixes, right? So it's going to be still cheaper, less effort, and we can still get the assembly functionality we need. So why not do that? So that was the inspiration. And sorry. So we basically formulated a one-dimensional chain, assembly chain, so which is the simplest we can start with some given assembly specification and confidence level that is required. And the decision variables here for us were this matrix X, which is the assignment matrix. So I want to decide which part should be built with which set of process parameters in additive manufacturing. And we also had this P's, a vector P, which was reflecting the confidence level of the components, and which was eventually translated as tolerances and the defect rate of the assembly at the end, okay? And then we formulated this optimization model, like simple optimization model with different constraints with respect to the assembly confidence level, assembly specification, and manufacturing decision making. And we had some nonlinear constraints which we handled, converted to linear constraints, etc. So the methodology we adopted for solving this, first we use bootstrapping. So bootstrapping is a statistical technique. Basically, when you have limited observation, it allows you to kind of estimate the population parameters based on limited observations. So for additive manufacturing, we knew that if we for example, want to have an idea of the error distribution, we cannot just simply go with normal distribution. So we had to kind of estimate this based on some limited observations. And that's why we use the bootstrapping. So the bootstrapping technique was used to calculate the confidence intervals for each of the elements of the vector P. And then we kind of repeated that simulation T times and then got the weighted arithmetic mean of those values to get the upper and lower bound for the confidence level. And then we basically did that for all the different parts we had. We use cyclic optimization to solve the optimization problem because this was a multivariate optimization problem. The way that the problem was formulated, the objective function and the constraints and the decision variables were kind of the way they were related. It was really hard to use any other optimization to solve it. So this was the solution we came up with. So multivariate optimization, what it does is that it kind of fix one of the, for example, here we had two decision variables. So fix one of them and then solves the optimization with respect to the one remaining. And then once you have a solution, you fix that one and then again solve the optimization with respect to the other one. And you just keep going back and forth with these cycles to kind of converge to the solution you want. And finally, once the optimization was solved, so we had the matrix X, the vector P, then the elements of the vector P could be translated to these tolerances using this formula. And you can see that the tolerances that we could achieve using this method were not necessarily symmetric. We could eventually end up with asymmetric tolerances. And the last step was tolerance scaling. So we went back and see if there's any unused tolerance band. And if there was any, we actually went back and kind of basically distributed that among the components to kind of further reduce the number of defect rates at the end. So we used a weighted approach to do the distribution. So this is again a simple illustration of the results here for you. So as I said, we use a one-dimensional chain. We use 5 components. We were actually printing these components that were with different nominal dimensions that we were interested that were contributing to the chain of the assembly. And the assembly specification confidence level was given to us. So we actually used our methodology to basically find the tolerances for each of the components plus the process parameters, the additive manufacturing process parameters that should be used for each of those components individually to not just, for example, have the lowest cost possible, but also basically achieve the confidence level and that assembly specification as we wanted. So we even compared our method to a bootstrap assisted semi-exhaustive search. So you can see here, for example, the blue one is our method and the orange one is the bootstrap assisted semi-exhaustive search. You see that the unit cost for the assembly, right, for our approach, the minimum max average, right, is always consistent, whereas for the other one, you need to do some exhaustive search and still we couldn't really achieve that very well. So in terms of the computation cost, our method was still faster than the exhaustive search. So again, this was the first step towards doing tolerance design with additive manufacturing and how to use a smaller amount of data points to do tolerance design, and also how to do tolerance design jointly with manufacturing decision making, not in a separate way that it was like traditionally done. So all these methods that I talked, you see, they had some components that were model-based and some components that were data-driven. So model-based, generally, like you have optimization models, you have numerical models, like anything that comes from domain knowledge or physics of the process, or you have like a theory of that, you know, we call it model-based. And model-based approaches, they're generally interpretable and reliable. And with respect to basically capturing stochastic behavior, they're not as good as data-driven approaches, right? So they're generally more on the deterministic side. And because of that, you know, generally they give us lower accuracy because you have to make a lot of simplifications and assumptions when it comes to model-based approaches, right? Now, data-driven approaches actually on the other side, on the other hand, we have seen them that like they can do magic, especially if you have good amount of data that you can fit them, they can get you very accurate results. However, on the other hand, they have they have this reliance on large data sets, right, which is very costly, which also very complicated, especially for additive manufacturing. We know that the data acquisition, the data gathering, pre-processing, all those steps are very time consuming and also very costly. The training of data-driven approaches is also very costly, and eventually you end up with a black box that are hard to interpret. So basically the spot that is very pleasant for researcher is that this spot which is in the middle of them, the model-based and data-driven approaches. And this has been something that many people already have been publishing about, like in the literature. So let me get into an example with respect to thermal signature and melt-pool modeling in additive manufacturing. So you see that there are researchers, right, using analytical models or like simulation models, for example, to extract thermal signature or thermal behavior in additive manufacturing. So these are really, really useful studies. However, you see that they're generally limited to very simple geometries, right? And it's hard to kind of generalize that to more complex scenarios. They're also very time consuming. On the other hand, those that rely on data-driven approaches for thermal signature or pool modeling, they have to deal a lot with the data acquisition, data pre-processing, you know, and all those steps still very time consuming, and also the model, as I said, they end up with it's not as interpretable as the physical models here, right? So the question that has recently been emerging in the literature is that can we truly integrate model-based and data-driven approaches? And the answer to that is actually yes. So we see that many researchers, as I said, they're looking at the sweet spot between model-based and the data-driven approaches, which is in that center, in the middle of those two circles that I said. And this has been done actually in the literature, I don't know, since like many, many years ago. The way that they do it, I call it hybrid methods. The way they do it is that, for example, they have physics and domain knowledge data, and they try to incorporate this knowledge into data-driven here, for example, neural networks. The way they do it is that they basically get the output of the physical model and put it as the input of the neural network and vice versa. So it's more like a sequence-based solving and interference of the problem rather than really fusing the two together, right? And of course, this is most common in the literature, but in terms of the fusion and interpretability is less effective, right? So we see that since 2020 or 2019, and the rise of the PINs, physics-informed neural networks, and how the manufacturing community is now trying to kind of evolve together with that, and how we can really bringing that knowledge of pins, you know, into the additive manufacturing community as well, to kind of make the learnings really physics informed, all the learning and inferences physics informed. Now, so you see that we're evolving or basically moving towards physics informed learning and inference, where the physics and domain knowledge are going to be infused into the neural network architecture and parameters. So either, for example, by manipulating or changing the activation function or loss function, or even the design of the architecture of the neural network, which that corresponds to the physical model, right? You want to kind of fuse those knowledge into the data-driven method. And why this transition to like actual fusion is necessary, because as I said, for additive manufacturing there is a different application domain, right? So we're dealing with mass customization, not mass production, and we're also generally dealing with noisy and scarce data, right? So when you have mass customization, you want to make sure you have models that are interpretable so that you can easily transfer them from one design to another, right? So that's why this truth infusion is really needed for additive manufacturing community. And the scarce data also complicates things, because now you have limited data to train your neural network. Of course, neural networks by themselves, we said if you have good amount of data, they can do magic, but without data, they might not be as useful. So that's why it is important to bring some form of additional knowledge to them by, for example, incorporating or fusing the physics and domain knowledge into them to give them a better understanding of the process so that they can give us more accurate results. So I remember PINs, the physics-informed neural networks idea, that when it emerged in the literature, and they're very good PDE solvers, the way they actually work, they kind of work on manipulating or augmenting this loss function. So they change the loss function of the neural network, right? And after that, a lot of researchers are trying to find other ways to fuse the physics and domain knowledge into the neural network. And our group is actually trying to do so. But we're basically going a different route than majority of the literature. So we're working on the architecture design. So we're kind of trying to design the architecture of the neural network with respect to the physics and domain knowledge of the additive manufacturing process. So as I said, the three different methodologies that are more common in the literature, I mean, the two of them that are more common on the left, you see the input feature engineering and loss function augmentation. And as I said, this loss function augmentation is what pins are using in the literature. They call them pin, but they're made based on the loss function augmentation. Now, another one is architecture shaping, which is what our group is trying to do. So we try to see how we can infuse the process physics into the architecture of the neural network to make it more interpretable as well. So the idea that we're kind of leveraging in our methodology is a deep unfolding idea. So the neural network that we're kind of building, again, we call that solution architecture-driven physics-informed deep learning. We call it APIDL, which relies on the deep unfolding methodology. So this methodology says that if you have an iterative algorithm or optimization model or anything that is iterative, okay, and it can be iteration with respect to anything. It could be temperature, it could be time, it could be iteration with respect to, like, for example, the optimization cycle. The iterations could even reflect to like the different states of the design. They could reflect to, for example, the layers of the 3D printing, anything, okay? So anything that is in an iterative form. If you have such model that can map the transition between a k-1, so iteration at k-1, and iteration at time k, or whatever, iteration k, if you have this mapping function, and this mapping function, of course, should be nonlinear, because if it's linear, you don't need neural networks to solve it, right? So it has to be nonlinear in some form. Then what you can do is that you can actually unfold each of these iterations into one layer of the neural network. So the weights and biases of the neural network, you can attach to the coefficients of your physical model. So in a way, when you're solving your your neural network, or I mean, you're training your neural network, you're solving for these weights and biases. It's like you're solving for the coefficients. So the weights and biases give you information about the coefficients of the model, and that's why they become much more interpretable. So it's not going to be a black box anymore. Also, the connections between the nodes actually comes from the physical model. So for example, if from one iteration to another, you know that there are two parameters that are related to each other based on some coefficient, right? So you can put the connection between them. If that connection does not exist from the physical model, you don't need to put it. So that's like a additional computation that the model does not need to learn, because based on physical model, you don't need that information or that connection at all. And the activation of each of these actually comes from this nonlinear function as well. So the form of this nonlinear function, whatever that form is, basically that inspires the activation as well. So following this deep unfolding methodology, you will end up with networks that are super sparse, like you see at the bottom. So instead of fully connected ones, you get sparse networks like you see in the bottom. So it makes them very, very suitable when dealing with limited data. So they can be trained with limited data, and they can perform better than fully connected networks. In terms of computational efficiency, they're much better also. And as a result, they're good candidates when it comes to real-time machine learning and quality assurance, which is basically what is needed for additive manufacturing, and a lot of researchers are working towards that. So let me see. Okay, so we actually did some collaboration with Argonne and with some of our collaborators in Texas A&M, Ohio State, and they were actually getting synchronized high-speed infrared X-ray imaging experiments. I think the material they used was a titanium alloy TI64, and they were basically doing different tests, both on like a substrate, like only laser on the substrate, and also on the power bed, and it was just like a single layer, single path. And basically they gave us the data, and we were actually trying to implement the APIDL method that we had on the data they provided us to see whether we can capture the temperatures, and first of all, and whether we can do it more efficiently, especially in the limited data region, whether we can do it more efficiently than other methodologies. So of course, we selected different points on the laser track, and then try to do prediction of the temperature with our APIDL. So of course, there was some good match, between the experiment and our model. especially at the peaks, we saw some inconsistency in the prediction results. Our hypothesis is that, for example, one of the hypotheses is that this titanium alloy, actually, I think the melting point of that is around 1877 something Kelvin. So above this, you see that there is a transition to liquid phase, and that transition to liquid phase is not captured by a physical model. So the physical model already did not have that information. So if we, for example, incorporate some of that into our model, it might be able to capture this peak much more accurately. And it's also important that I highlight here that the data that we're using for training here are very, very small. Okay, so it's not the standard size of data that people use, for example, when they use neural networks or any other data-driven approach. We're using very, very small data points, and we can still get good results. So I'm going to compare it to other data-driven approaches for you to see how our method actually performs. So for example, we compare the API deal with the artificial neural network. So if we use the same data points now with artificial neural networks or regular deep learning, and then we use the LSTM, of course, is very good for time series analysis, and the SVR and ETR also. So SVR specifically, for example, is very good for when you have like limited data. They have proven to be very good models that can handle limited data. So you see that our model still came up with like a less error despite the very, very small size of the training data set. So the error was significantly low in terms of the computation time, somehow in the middle. So not the best, but not the worst, but it's still manageable. It's just a matter of seconds. But again, the question was that, you know, the main argument about API deal is that it's very, very good when you have limited data, right? So we wanted to see or test that basically how data efficient the API deal model is. So what we did is that we kept reducing the number of training data. And I'm sure like people that are working with like, you know, this thermal modeling and additive manufacturing know that, for example, having 100, 200, 300 data points for training is not much, right? So we actually reduced it really low until 200 data points only for training. And this is a very, very like a limited or scarce like data region that is not really common in the literature at all. In literature, they're generally above like a few thousands or even, you know, million data points. So you see that, you know, the API deal, which is the blue one, kept outperforming the other two. And these two that we selected, the ETR and the LSTM, these were basically outperforming the others. So these were the best two candidates. And we still kept outperforming them using the API deal approach. So you see the API deal approach can do really good predictions when we have limited data scenarios. But as this training data is increased, of course, you can imagine that all these models, they're going to get better and better. But one downside to the API deal is its computation time. So you see that it seems like it's exponentially increasing. So if the data becomes really large, it might not be a good candidate compared to other methods. But when the data is really small, then it's going to do much better than the other existing methods. So yeah, with that, actually, I'm done. So I just want to acknowledge the SmartShare Lab, my students that made this research possible, all our collaborators. Yeah, and I'm happy to answer any questions. Thank you so much.
Thank you so much, Azadeh, for the interesting talk and much details about the data-driven models. So we will open the floor now for questions. So if you have a question from the faculty, please feel free to unmute yourself and talk. And then from the students, please send your Q&A questions in the Q&A box, and I'll read them as they go.
Thank you very much again, Dr. Haghighi. Ala, I'm trying to see the Q&A. I see the chat, but do you see the Q&A? Okay, I found it. Here we go. So, all right. Yeah, I guess if you guys have any questions, you can unmute as well or ask us to do so. I don't know if you have that option.
Hello, Hussein. Can you hear me?
Yes, yes, go ahead.
Okay, thank you so much, Dr. Azadeh, for the nice talk. I guess we both suffer from the last name, difficult last name. My last name is Hakshinas. I always have issue with that GH, which I guess is a typo. It should be Q. Anyhow, A very good talk. My question is a naive question, therefore do not laugh at me. This is not my area of research. My question to you is here. If you can explain what you explained in last 45 minutes in a simple language, in a couple of minutes, in a non-technical, I would say, language for a high school kid, something like this. And in particular, since I'm an experimentalist, I would like to see what is the correlation between your research in whatever you presented with some experimental work, how we can make this connection between this research and some real experimental work on either additive manufacturing or fatigue or something like this.
Okay, yeah, thank you. Thank you so much for the great question. Yeah, and the last name thing, I agree with you. I can resonate with that. But yeah, that's a great question. So basically, just the 1-2 lines, if I want to summarize everything. As I said, we have to move towards data efficient learning. So especially in the additive manufacturing, I'm not really familiar with other manufacturing processes, but for additive manufacturing community, especially because everything relies on like customized shapes, customized designs and everything. So the transferability of all the models we have, any type of like model, any type of physical model, any type of data-driven model, the transferability of that and scalability of that to different scenarios, different geometries, maybe from one additive manufacturing process to another is very important. And this is something that is still lacking in the literature. So it is important to learn how to create that transferability, how to make models, data-driven models that are interpretable, that you can easily transfer them from one process to another without actually needing to go back and, you know, getting all the data again and retrain everything, right? So we want to do that real fast. And the way that, you know, recently we have seen people are trying to do is that to really try to think of ways that data-driven models can be fused together with physics models. So any type of like, if you, for example, you said you're experimentalist, right? So you have a lot of domain knowledge about the process. You have, for example, an understanding that based on your understanding or your experiments, if I, for example, increase this process parameter, then the output, for example, will change this way. Like, for example, they're positively correlated. If you have that knowledge, and let's say if you want to have a data-driven model that, for example, is being trained on basically predicting that output, right? You can incorporate that domain knowledge, even though you might not have a physical model for that phenomena to explain that phenomena, but you can incorporate it into data-driven model. So how can you do that, for example? So let's say your data-driven model predicts that this output, once the input actually goes up, the output goes down. But from your experience, your experimental experience, you know that these are positively correlated, okay? You don't know what's the relationship, why is the physical phenomena that causes this, for example, fully, but you know that they're positively correlated, this input and the output. So if your model actually is trained or is learning the opposite, you can actually incorporate some form of penalty function into the loss function of the neural network to kind of transfer your domain knowledge into the neural network or the data-driven model. So right now I see many manufacturing communities are starting to do so, to get all those domain knowledge experience from the experiments that they're performing, or whether if there's any physical model or not, how to kind of bring it into the data-driven world.
Perfect. Thank you so much. I like the answer. Thank you.
Sure.
So we have a couple of questions in the chat. So Jamal Ansari asks, thank you for presentation. You mentioned loss augmentation. Is this the same as weighted loss function?
Yes, correct. So that's what we called it, you know, in our work. Yes, loss augmentation. But it's yes, loss function, changing the loss function. Yes.
And another question from Hussein says, thank you for your presentation. I was wondering why you are searching for a single data-driven method. Why not using all or some of the models together to get the results? This is partially because some models are safer for long-term modeling and are safer when we I think I just lost the remaining. Let me see, enlarge my screen. Yeah, safer for long-term modeling and are safer when we add new data.
So, so let me, I might not have understood it very well. So the question is why we're not using a group of methods, right?
Yes. Yeah.
So yes, that's a good question. But you see, first of all, with this API ideal model that we're proposing, so again, this is an innovative way of bringing the physical model into the neural network architecture. We initiated this research by seeing whether the claims we have about this API ideal that it can work really good, for example, with limited data scenarios, whether the claim is holding or not. Okay, so we wanted to just test with some other data-driven approaches first. So the next step, as you said, we want to actually go into more complex cases. So we want to compare API ideal with other now physics-informed approaches, right? So we can, for example, have the same neural network based on loss function modification, right? And then we can compare it with the API ideal to see which of them would perform well. Or you might have a set of or group of models, for example, together, and then we compare it to the API ideal. Again, the idea is that the API ideal or the hypothesis is that it can actually perform well because of the way the architecture is shaped and it's sparse. It has a potential to do very well for limited data scenarios. And eventually you can imagine, for example, in comparison with other advanced techniques like GANs that are recently emerging, API ideal, still we suspect that it's going to do better, for example, because GANs, for example, there are two different networks, right? There are two networks that one is basically has a discriminant part and the other one, so you have to first have the network that generates the outputs and then the other one that, for example, is a discriminant and figures out whether the output is good or not. And once you have that, then that has to go into another network, right, that is doing the training. So you eventually deal with two networks, whereas for API you only have one network. So we still suspect that compared to other emerging methods like GANs, API ideal has a potential to do better, especially in the limited data region.
Thank you. And I think it's a follow-up question. Why are the hidden layers, or what are the hidden layers doing in neural network? How you form them in the data-driven model?
Right. So this hidden. So let's say you have, as I said, like a model that is iterative, right? So you start with iteration at iteration 1, iteration 2, iteration 3, iteration until iteration, for example, 100, right? So each of these, you can actually map each of those iterations to one layer. So all the hidden layers basically are the iterations of your model, right? So iteration, for example, 2, 3, 4, 5, 6, and so on. So depending on these iterations you have, right, you will actually build the architecture with different layers that each layer reflects each of those iterations, basically.
Thank you. And I have a follow-up question
Sure.
for the data-driven models. So basically, the data-driven models depend on a experimental identification of the input and output of the process, right? And since we may have multiple process, multiple machines, and multiple materials, all of them can have, different input, different output. But I think maybe it's a question for the future work, is how you see the federated learning when it comes into the data-driven models. Like, is it something that's actually worth investigating and going for, especially if you have data from different sources, from different manufacturers, different machines, you merge them in your model and try to predict for each one what's going to be the model output?
Yeah, that's an excellent point. So actually in my group, we haven't done any research on federated learning, but I've seen that there are researchers that really are working on that. I think there is a lot of potential with federated learning from different sources. The issue that is kind of concerning is about the security of data. And I've seen, again, many researchers are trying to because you're sharing the data, of course, you don't want to pass along all the information that years of R&D and efforts from your company, but you also want to share that data so that others can leverage it and train models. I think for many people that do data-driven modeling, the limitation they have right now is access to data. Everyone is trying to get access to the data and finding good data, data that are useful and usable. It's very challenging. So federated learning definitely a solution, but I don't know, the cybersecurity part is already a concern, and I know many researchers are trying to address that. Yes.
Thank you. And there's a full another question from Muhsin. Thank you for your informative presentation. Have you introduced your data-driven prediction model as a commercial software for mechanical setup or improvement of printed part in AM process?
Thank you for the question. So we haven't yet. So the issue is that, you know, we just started this idea. So we have been trying. So right now, for example, we have been working on single layer, single track, right? So you can imagine that when you have single layer, single track, the iterations we have considered here are time. So we are doing the unfolding with respect to the time. But eventually we're planning to go and do the unfolding with respect to the layer. So we can do layer wise modeling, right? Instead of like, for example, going in one layer and doing like iteration of time, we can do iteration of layer. And this is where we're going. Hopefully if we get there and, you know, if we can manage to do that, because that requires changing of the way we have formulated the problem. But if that is done, you know, we would like to have, for example, a commercial software, for example, out of the API deal for sure. But yeah, not at the moment.
Thank you. And there's a question from Shiva. Thank you for your great presentation. I believe the proposed approach is for large-scale additive manufacturing. I was wondering if your approach is applicable to microscale, or your approach is applicable on microscale.
It can be done for any scale, right? It really depends whether you can have for whatever, for example, scenario you have. Do you have any model that has this form? If yes, this model can be used for sure. For example, you can just use the deep unfolding on the just optimization alone. Let's say you have a gradient descent optimization problem, right? And this is, again, is not even related to manufacturing, right? But we just have a iteration model, iteration optimization model. And the gradient descent, you can actually unfold the gradient descent on layers of neural network and then converge much faster. So again, using this architecture-based deep learning methodology that we're proposing. So it can work with any scenario as long as you have a model that looks like this and has a nonlinear like function that maps the iterations together.
We have
Thank you. Yeah.
one last
Last
from
question. Yeah. How you link numerical modelings with theoretical modelings? For example, slide 6.
The numerical modelings with the theoretical modeling.
Yes.
So I assume so. I mean, the numerical models or like theoretical models, they're all the same. So I categorize all of them as model based, right? So those numerical models, theoretical models, all are this term, this model. If you have to first, if let's say you have a numerical model that has this form or can be transformed to this form, right? Then you can actually connect it to the neural network. So we're not really connecting theoretical and numerical model together. We're just finding a theoretical or a numerical model or any type of model that is iterative in this form. And then we try to connect the parameters of this iterative model with the weights and biases of the neural network. So we try to kind of define an architecture based on that model.
Think.
Can I ask one last quick question?
Of course. Yeah. Go ahead.
Again, thank you for the nice talk. I saw in one of your sponsors, you have listed NIST. You are working with NIST on a different project on fatigue. My question is that what would be the interest of NIST on this DNN? Because NIST is toward the standardization.
Right. So yeah, so that project that I'm working with NIST is not related to the API deal directly, but yeah, I mean, we have been targeting NIST. There was like, they had a call like a year or something ago on additive manufacturing, and we submitted there, but it was a very competitive one. But I mean, we are pursuing this physics informed, like the architecture driven physics informed deep learning methodology we have, and I think they are very interested. However, I think it's kind of the idea of physics-informed learning is kind of now being saturated, meaning that everyone is now using it. I was actually talking to one of the program directors, and it's the program directors, and he was actually saying that if I get one more proposal with physics informed, I'm going to be so mad. So it's just, I think everyone is trying to, and I mean, that is good because everyone is excited about it and they try to kind of leverage that. But I think how to kind of separate ourselves like from the pool of all these people and, you know, bringing up something that is very innovative, I think that would be very interesting. Yeah.
Thank you very much.
I don't know, Azadeh, you say physics informed, like the current NSF future manufacturing call needs physics models, right?
Right.
So still there's a place for it.
Yes. So it's exciting. There is a room, you know, for everyone to collaborate. I mean, do research on this topic. But again, everyone is trying to, you know, have a spot there. So, yeah.
Well, thank you very much, Dr. Haghighi. Thank you,
Sure.
Dr. Katabi, for moderating this. A really great talk. Outside of my field, but definitely looks fascinating. Hopefully, we'll get the chance to host you in person in future. We're not that far from you guys, so and we have a lot of people doing basically additive manufacturing, shape memory alloys here in the department. So that would be great.
Sure. Thank you so much. I appreciate it. Yeah. Thanks for arranging this and for all the students attending and everyone here. Thank you so much.
Thank you, Azadeh.
Wonderful.
Thank you for your time.
Wonderful.
Sure,
Thanks.
thanks.
Yeah, this concludes our seminar, and everyone have a wonderful weekend. Thank you.
Yeah. Thank you. Thank you, Allah.
Yeah,
Appreciate
thank you.
it.
Bye.
Bye.